Hello everybody, and thanks for joining us for this discussion about why Rust won't replace C just anytime soon. So first off, I think most of you are very aware of feedback, so I won't spend a lot of time on this, but obviously we're professionals from a training perspective. And what's happened quite recently is, if you look at the market studies, etc. So this is the market study that Embedded and EE Times does every year. We can still see in the embedded sector that C massively dominates, and that's been pretty fixed for many years now, and with C++ being a second language there. What's interesting looking at this is that, of course, Python is appearing third there, and this then, of course, brings up that ongoing question about what do we mean by embedded from that perspective. In this context, really, we need to differentiate, and we internally tend to use the term embedded and deeply embedded. And I've distinguished those. So deeply embedded, we're normally talking about something we regularly call bare metal, so something like a Cortex-M system. And that means we've not got an MMU, so we can't run something like Linux. So from our perspective, embedded quite often is a Linux, maybe Android-based system, and deeply embedded is our traditional C model. May use an real-time operating system like FreeRTOS, may not, but could be a bare metal sort of foreground background route. From a build perspective, then possibly you're using something like Make. More lately, you might be using something like Ninja, but obviously Make or CMake or something beyond those different systems. So first off, a couple of things. I won't proffer myself as a Rust expert by any stretch of the imagination. I've been working with Rust now for about 18 months. And it was one of those things with bubbling around. And in that time and in the experience of working with Rust and learning Rust, is at the moment I feel that Rust will not replace C as the primary embedded programming language, certainly anytime soon. And what I'd like to, as we work through this webinar, is look at why I believe that's a particular case at the moment. So first off, if we look at current languages and embedded languages, and this is very much from a deeply embedded perspective, then we know that C dominates. Second, we can see that C++ 03, and more recently, we've obviously seen the transition to modern C++. So typically modern C++ is anything past C++ 11 is an area of use within that deeply embedded and deeply embedded area. And the question is, if we had to pick a third language at the moment, what language would fit in there? And for deeply embedded, I certainly wouldn't say Python fits in there. Python is normally using some sort of virtual machine. Suits Linux fine, but not deeply. There are obviously things like MicroPython out there, but I'm not really considering that. So at the moment, I think you'd have to consider Ada being the third language in there at the moment. Ada's still around. It was interesting at a recent open source conference, there was a whole track still on Ada, which slightly surprised me. And my background originally goes back to Ada in the late 80s and early 90s as that. So the big question is, can Rust be a language that becomes another player in this particular market, in the deeply embedded market associated with it? So if we start with what Rust is and look at its project goals, so the outline they talk about, and this is a statement from the actual Rust site itself, is to design and implement a safe, concurrent, and practical systems language. So important there, first off, systems language. So as with C and as with C++, none of them were actually designed to be a deeply embedded programming language. They're all coming from that environment. Obviously, C was a porting language, C++ was very much a simulation language. But interesting that Rust has been designed as a system language. It's also a relatively new language. So if we look at even languages like Java date back to, they're 25 years old now. Python is that similar frame. Obviously C++ is late 70s and C in early 70s. It's only been around for about 10 years, and it came out of the Mozilla group in that sense. Now, when you look at Rust and you go and read when it's ever put up there, they talk about their success stories, and probably the headline success stories they tend to talk about is, first, obviously, Firefox. Firefox is obviously developed by Mozilla, and there's a huge swathes now of the engines behind that are now written in Rust, and that's led a lot of the Rust development behind that. Interesting is the stuff by Dropbox. So Dropbox, which I'm sure many people are familiar with, I use Dropbox on a daily basis, is they've got an interesting article, it's a wide article if you Google it, where they actually done a lot of work in Google Go, but found they weren't getting the performance of Google Go. Now, Go, like Python, uses a garbage collection, and they were seeing performance implications with the use of the garbage collection, which obviously anybody in the embedded field and the real-time field is very much aware of, the aspects of why we can't use garbage collection in real-time systems. And they transitioned from Go to Rust, which is, again, quite interesting, given that Go is considered a modern language as well, and a modern systems language as well. And finally, the other big headline is Microsoft, and they did a big analysis of their looking at their patches, and they found that 70% of all their patches are memory-related bugs. And because of that, they chose to then look at Rust as a language to try and start addressing a lot of their infrastructure work or reduce and eliminate many of these things, which is great. You look at all these and they're good headline ones, but of course they all share something in common, is none of them are embedded, and what I would call an embedded. So Rust, like I say, has been knocking around, and over the years when I've been training people and talking about C and C++, people have asked me quite often, what do I think about Rust and what's happening? And it's been there, and I've been looking at it, but what was starting to get more interesting is suddenly I'm seeing some of what I'll call the embedded players starting to talk about Rust. So last year, Wind River made a big announcement about the new generation of VxWorks, their real-time operating system, and just found it was interesting that not only they talk about C++17, which is great, they're on the leading edge there with Boost, also Python, interesting, but they put Rust in there, and it's one of the first times I saw an embedded, and what I call a mainline embedded company, a provider of embedded tools, talking about Rust in that same collection as well. Also Nordic, people are very familiar with obviously the Nordic set of devices, very good for and used quite heavily in a lot of the IoT-based areas. And there's an interesting paper there where they're talking about Rust and the potential of using Rust in these deeply embedded devices to eliminate and build safe and secure systems, which is an easier alternative to using C and C++ in those. So suddenly we're starting to see that interest in the deeply embedded space. The other thing that's always pushed by Rust is Stack Overflow do a development survey every year, and it's been running for many, many years now. And Rust, for actually the last 5 years now, has always been classed as the most loved language by the Stack Overflow community up there. So you can see this head is 83.5% of there. Interesting, if you look at the most dreaded language, then C becomes number 4 on that particular list in there, so quite high up. And you can see C++ being slightly further down on that. So it does seem one thing about people who are committed to Rust become almost evangelical about it, and certainly it's something when people, and the people I talk to have been using Rust, is there is a real appreciation of the language in there. Now, certainly from my perspective, when looking at deeply embedded, there's a lot of languages I've just dismissed, things like Go, etc., and Swift and Kotlin, because they have, for my use, they have to be able to, say, replace what C does today. And the first thing about Rust is it's a compiled language. So as with C, and the basic memory model of Rust is the same as C. So there's nothing unfamiliar there when you start programming Rust that you wouldn't be familiar if you understand the C memory model. So it uses a stack, it's got statics, and it's got that sort of lifetime model where you've got persistence of the program, and the deeply embedded work has been done that the heap is optional. So it does have a heap-based model, as you would do in a hosted language, as C does with its malloc, etc. But it does have an embedded build where the heap isn't required, which you find with a lot of languages that are put forward is they have to have dynamic memory to work. And obviously that's a limiting factor for a lot of smaller real-time embedded systems, especially non-Linux-based systems. Rust itself at the moment is built based on top of a toolchain called LLVM. You may be familiar with that. There's something called Clang. So Clang is a C language front end, and that's used heavily on things like OS X. So Microsoft, the Mac uses the Clang environment, and ARM, for example, they moved over a number of years ago to using the LLVM toolchain and Clang as their major compiler for their C and C++ compilers. So it fits in with the ARM architecture very well. So the back end of all the compilation model of Rust is exactly the same as you get with C and C++. So it has a very familiar model when down on the target in terms of things like map files and layouts, and using exactly the same sort of tools at that back end that you'll be using in a deeply embedded C environment. So in terms of linker scripts and laying out the memory aspects with that. So that side I felt very, very straightforward. It was a direct, correlation with all the C work. There was nothing new and no additional overheads as well. There's no extra runtime overheads in there, which is always the worry in some of these particular languages. From a language perspective itself, the base level would be very familiar to the C program. So coming from very much from a C perspective, you've got your integral types and the integer size, and certainly with C99 having standard int, you've got that basic same set, the signed and unsigned 8, 16, 32-bit types. It calls something isize, which is your typical int, and it's got the usize, which is your typical unsigned, which are the machine-specific integers, so 64-bit on a 64 machine and 32-bit. The real numbers are probably better defined than the C model, as they simply have an F32 and an F64, and they map directly onto the single precision, double precision numbers. It has a Boolean model, more sort of closer to the C++ Boolean model in the fact it's a true Boolean, and they have an enum. Now the enum it can be very basic, the enum that you have in C, but actually, again, it's probably closer to a C++ enum than a C enum. Other familiar concepts from a programming perspective is the basic control flow as you'd expect. You've got things like if statements. It has something called a match statement. That's the equivalent of the switch. It actually does a lot more than a switch, but your basic multi-choice selection, then you have this thing called a match statement. So that gives us our I just appreciate I've got iteration and selection the wrong way around, so I apologize for that. That gives, of course, your selection. The iteration one is we have a while loop. It doesn't have a do while loop. But interestingly, it has a loop construct, which is just the equivalent of a while one or while true loop. So it already has that built into the language. And the for loop, again, is what I consider a true for rather than the sort of bastardized for you get in C, because obviously the for loop in C is really a while loop in disguise, which I think most people are aware of. And that obviously has its implications in terms of building safe and secure code, where this is a for loop. Closer to the range for loop you get in something like modern C++. It has array constructs, it has functions as the building blocks, it has structs, and as I mentioned before, enums. So to get going with basic Rust from a C perspective is actually relatively straightforward, and there actually is a utility out there that does a sort of basic C to Rust conversion. So you can take a lot of C code and do a fair straightforward swap with Rust. However, there are a whole host of concepts that, as a C programmer, you're probably less familiar with or not familiar with. If you're using modern C++, or maybe you've done Python, obviously a lot of C people now have got Python skills as well because you're using it in things like the test environment, then some of these will be familiar to you. So first is the structs can be extended to form the equivalent of a class structure. So you have an implementation model. So it gives you that basic object model or class model you have in, say, C++, but really built on top of the direct structs itself. Rust itself doesn't use, the pointer model is actually based on a concept called references. And again, I won't spend too much time on these, and I don't want to get too much into the syntax of these, but just to explain some of these building blocks. And these are sort of a safe model in terms of that indirection we expect through pointers. It does have a support of generic programming. So Ada has generics in it. Obviously, C++ has templates. So it has this idea of generics. But rather than using, it pulls out the interface. So things like Java has interfaces, and in Rust they're called traits. So this is a nice model or a well-defined model for low coupling, and obviously for building robust programs and maintainable programs, separation of concerns, low coupling is key to a good architecture. And for this, it supports this idea of traits associated with it. It has a modular, it has something called modules. That's very akin to sort of the Ada package model. And the Java package. It's more than, say, a namespace in C++. It's close to the namespace, but actually has the ability to have both public and private models within that as well. It has the closure model that people may be familiar with. They've done anything like JavaScript or you've done modern C++. So this is the lambda model. This is sort of anonymous nameless functions which are used in a particular type of programming. And that's very common in functional-based programming. So one thing Rust does have is it's probably closer to some of the, it shares certain aspects that are closer to things like F in terms of functional programming. So if you're familiar with that, it's not my background, but obviously a lot of people there is a whole area around functional programming, and Rust has very good support through that, through a very strong iterator model and this closure model. The other thing I liked about Rust is the fact it doesn't use exceptions. Obviously, coming from Ada, my background in Ada and C++, both being using exceptions, and they have certain issues in the deeply embedded space. Obviously, we know that there has to be a certain degree of runtime overhead when we're using exceptions within that. Now, the modern C++ has improved on that. It uses a table-based model, but that does have an impact on the image size. Where Rust has a very strong error handling model, but not using an exception, so it doesn't bring that overhead to the runtime binary. So it keeps that runtime binary, but has a better, well-defined model than, say, C. Unfortunately, C doesn't really have any error handling, and each company sort of has to do it their own way. It does have macros. They're not really the macros you'd have in C, apart from when you may be doing token replacement, so using things like hash or double hash. It's more of a meta-programming model, which again in C++ you quite often use templates for. And so it deliberately, so that's quite interesting in Rust, that where you in C++ you have templates for generic programming, interface programming, and sort of meta programming, Rust has pulled those out into 3 separate ideas associated with it. So it's a very, very powerful language in its own set. It's not an OO language. It's not professing to be an OO language. So it doesn't do inheritance in terms of concrete inheritance. It doesn't do things like multiple inheritance in terms of concrete classes. So it's not trying to be an OO language, but it does give you a class-based language, and it does give you an interface language. So many of those important building blocks that somebody coming from C++ would be familiar with, probably less so from a C perspective. And at the base level, it has no raw pointers. And this is very important, and this is to do with safe programming. Now, I've got things saying not strictly true, and I'll explain later about that, what I mean by that. But because it uses this reference model rather than pointer model, now we know if you look at things like MISRA C, we know if you look at the cert coding guidelines, that pointers are still one of our major challenges when trying to build safe and secure code in C. It requires a huge amount of discipline from the programmer. It doesn't mean we can't build safe and secure C programs, but it really is a huge amount of effort, and like I say, in terms of peer reviews and code reviews and using static analysis to try and do that. And there are still certain key things that is very, very difficult to pick up, even say you doing static analysis within these. And I'll bring a couple of those out in a second. So take a simple example. Here's a little bit of C code. So this is, we've got a signed integer, 8-bit integer, and we've assigned it to 127. So we know that's going to be the maximum positive value. And there's a very good interview question saying, well, if I add 1 to that maximum value and I print that value out, what is the result going to be? And somebody who's maybe slightly naive or less experienced would probably say -1 to 8, because they assume it's going to go, it's a signed number, we're adding 1 to it, that means we get the bit pattern, hex 80, and that would give us -1 to 8. The correct answer should be that the result is implementation defined, or the implementation defined signal is raised. That's obviously what Annex G of the standard talks about. Now, obviously, in most processes, we will probably get -1 to 8, and that's a given at the moment. But the danger is where we rely on that. So it is perfectly legal for an application to, in effect, crash. So raising a signal, obviously, and if that signal is not handled, that's going to cause the actual program to crash. And this is where things like MISRA C become very important, because, of course, what they're trying to do is identify these areas. But this sort of runtime behavior, where obviously 127, as a literal is going to be seen, but if it was actually another variable being assigned, it's much harder. It's almost impossible statically to identify that type of overhead. So how does Rust deal with this sort of runtime problem? A good example is even quite recently there was, the common vulnerability database has a list, and even only last year we had another CVE raised in the, people may be familiar with the VLC media player. It's an open source media player. There was an integer overflow led to an out of bounds read, which led to a major exploit in the VLC media engine. So it still happens, and it's still happening. And every year, if you look at the database, you'll see that there are regular problems with numerical underflow and overflow within the language. So Rust takes an interesting. So here's an equivalent programming Rust. Again, I won't spend too much time on the syntax. First is we've got main. Main is the entry point, so again, very familiar. It uses fn to represent function. So again, it's a different syntax. And similar to modern C++, we've got this variable called val, which I've explicitly said as an I8 as a signed integer here. One interesting programming concept of Rust that is probably when you first use it, the most jarring to a C programmer, is that all of your variables by default are immutable, that being constant. And to make them mutable, you actually have to add the keyword nut, as I have done here. So let nut means that value can be modified. And your first reaction, or certainly my first reaction to this, is that this is really, I've never come across any other language that does it this particular way. But it's quite surprising how quickly you realize actually that by making things immutable by default is actually a really safe model and works incredibly well within the program. And it forces, again, from a programmer's perspective, to be absolutely clear about those things where you want things to be immutable and immutable. And we know from a C programmer's perspective that optimization, so the good use of const, can help the compiler with certain optimizations because it can effectively reduce and eliminate values in our system. So by defaulting to immutability, then it also gives the compiler opportunity to do further optimizations. So now we're getting 8-bit integer overflow. And the way Rust works, it has two models. When you build in debug, if I run that program with a debug build, what we get is a concept called a panic. Now, a panic is their defined model for the program in error. So it's where effectively the program has crashed, but using this well-defined panic model. And here we can see it's giving us a message saying attempted to add with overflow. And there are ways of panic you can define what that error message is within that. So that means that during debug, anytime we're getting overflow and underflow, we will get a program crash, and we can set up tests and test models to actually say this should panic and actually make sure our testing framework is detecting when panics. But obviously, runtime in a release, we don't want a program crashing. It's not good. So it does have, in this particular case, a model where if I run with the release model, then we get well-defined behavior. So in this case, we do get -1 to 8. So at least these sorts of areas are well-defined within the language rather than having these undefined or unspecified aspects that the C has always had, and is still one of the baggage issues we have with C when trying to build safe and secure programs. Other sort of things that you sort of get for free by using Rust are your basic lifetime checks. Now, so here we can see I've got a global variable that's telling me it's being unused. I've got a local variable that is saying is never being read, but it's been made mutable. So it's telling me that could be an immutable, that could be constant because it's not being modified. We've got a function that's never being called. We've got a variable again that is again needs to be doesn't need to be mutable within all these aspects. So these sorts of warnings we can get through our compilers if we set the right compiler flags. But the nice thing is these are all on by default, and you actually have to explicitly go and disable them if you don't want to use them. So for example, the second line in the program there, you can see the way Rust is a quick way of removing a warning is putting an underscore in front of a name. Will quiet, if something is not being used, then it will remove that particular warning initially. And there are lots of other lifetime. So there are more expressive lifetime checks. So take an example, if we go to MISRA, if we look at the MISRA rule 18.6, then that says the address of an object with automatic storage should not be copied to another object that persists after the first object has ceased to exist. And what is that? It's trying to say, of course, in a sort of slightly long-winded way, is this idea of lifetime management. And this is really what sets Rust apart from any other programming language I've ever used, is that it does compile time lifetime management rather than trying to do runtime where it can. So anybody who's familiar with testing, you might be familiar with this concept called the DU path. So DU path is that simple flow on the right-hand side, is saying that for any variable in our program, for any object in our program, it should be defined, it should be initialized. If it's constant, it should be read. If it's non-constant, it should be written to and read. And then finally, it should be destroyed within that. And for most of our program objects, and of course, for global objects, that's managed by the runtime system. They're defined as part of the program image. They're initialized, obviously, as part of the boot process before main, and they're destroyed when main ends. For local variables, of course, we get the same thing for any local variable. So P in this case being a parameter is equivalent to a local variable. Then it's being defined, it's being initialized on the call, it's being used, and then it's being destroyed. The problem here, of course, with this particular code is taken from the MISRA-C guidelines, is we can see that SP itself, the global pointer, then its lifetime, its DU path exceeds the DU path of P, and that now means we have an active pointer pointing at an object whose memory no longer exists. And that's one of our classic C problems, our C errors we get. And these are incredibly difficult to find and incredibly difficult to test for as well. There are certain static analysis tools that would do a good degree of looking for these sorts of problems, but they tend to be on the much higher end of the static analysis tools. Interesting, in Rust, it is pretty much impossible, and you can never say impossible, I'll explain why later, but to write code like this. At the base level, Rust will just forbid this sort of code because it would detect, using this lifetime management, that in this case, the global variable's lifetime exceeds that local variable's, and it will just fail to compile in that particular program. So it's a massive part of Rust, and certainly one of the challenges when you come to Rust, and I think this is true for everybody who's coming to Rust for the first time, is actually understanding how the lifetime management works. But if you understand runtime models, if you understand your C and you understand your C++, you'll appreciate this very, very quickly of what you're getting as part of that compilation model. And it is just stopping so many stupid mistakes or simple mistakes creeping into the code base. Now, another thing I'd like to bring is this idea of modularity. And coming from somebody who worked in the early days with Ada, having a proper, well-defined package model, is this idea of decoupling. So coupling is about dependency, and we know that one of the most, again, you look at things like ISO 26262, and they talk about a driver there to have low coupling in a program. So coupling is this measure of dependency, and Rust actually has an interesting model where it uses the file boundary as a boundary of encapsulation. So it does have structures that we mentioned can simulate classes. They can have their own boundaries as well, and they call these modules, and it does have a module section as well. But a file by default represents this idea of a module, and anything in that module again is by default private. So this is common to things like Java and Python use a similar model, is that the file represents this unit of encapsulation. And in building larger programs, and this explicit making things public and importing things becomes very, very important in terms of maintenance of a program and building libraries and building substitutable parts of this. So again, it has this very clear model for import, export, and making things visible and controlling that level of visibility within the program. And here I've used the explicit name. I said, that there's a function called div that, as you can guess, is taking two 8-bit integers and returning a signed 8-bit integer. And that module itself then is being brought in, and you can use various things. You can use a use directive to reduce the sort of the namespacing model that C++ programmers will be familiar with. So I've certainly again found that in terms of building larger programs, very familiar, certainly very familiar because of the Python work I've done in the background and the Ada work I've done in the background within that. Another area of Rust is build systems. So a lot of programmers, certainly programmers who are used to using IDEs, so things like Kyle or IR or even Eclipse, the build system there quite often is hidden from you. So the build system obviously is what we mean by that is the program that pulls all of your C programs, your C code together, compiles them all, links them into a single image, and then finally gives us our ELF file or our binary. For a lot of people, that's just doing build from a command line or pushing something like F5. So again, if you're using something like IR, you just say build and you get an executable at the end of it, your downloader executable. Under the covers, again, doing explicitly, then make is the historic one, the GNU make, which of course is just a C program in its own right, and you build your make files. More recently, CMake is probably the dominant make system used in C and certainly in C++ as make. But of course, CMake and below that Meson, they're both meta makes. So they will create, so CMake will create a make file for you, which you then make. But they also, now we have this newer build system a lot of people are moving over to called Meson. And the benefit of Meson, it certainly seems to outperform make as a basic build. And anybody who's been on a FEBAS programming course will be familiar that we use Scons. Scons and Meson are both Python-based build systems. So one thing that you've got is a lot of choice, and this is only a fraction of build systems you have in there, but people have to be responsible for this. Rust has a single build system. This is part of the Rust ecosystem called Cargo. So Cargo does all of that dependency and that file dependency for you. It also manages external libraries, and those libraries may be local to your machine, local to your network, or they may be in even a GitHub repo, or there is even an open source sort of Cargo IO site where people can publish what are called crates. Crates are effectively libraries in Rust, and it has all of that management to pull in libraries, and even has version control and versioning management of crates to ensure that you're having crates of a certain version. So the upside to that is that you only have to understand one build system, and this is, and actually for most programs, you have to understand very little about the Cargo build system. Now that there is one criticism, reading around and looking at people, and some of the stuff they said is saying that the one downside of this model is Cargo is relatively slow, say, compared to something like Ninja for large applications. And I know there's a lot of work being done in the background to improve the performance of Cargo. So that's something to be aware of. That and here I'm talking very large systems, millions of lines of code, etc. Not your smaller embedded system where you may only be in the 100,000 lines of code, etc. So I say, so that's a pro and a con. I like the fact that there's a single build system there. It's very simple. It's very intuitive. It does all the version management for you. Where things like CMake and Scons, you fight them for years trying to get these things working correctly, and somebody has to be responsible for the build. Another thing that is quite interesting, ticks a very good big box, is that there is built-in interoperability between C and Rust. So that means that we don't have to throw away all the C stuff we have as well. If we've got good C libraries that we want to utilize, then we can use those straight away in a Rust program. Or alternatively, you can start to migrate or introduce parts of in a C application where the main is in C, is to start bringing Rust code. So Rust and C can co-reside in the same image, in the same application within that. And this is called the foreign function interface within that. Now there are certain limitations. It works better with C than it does with C++. It's much more of a C thing, but it's a relatively straightforward thing. And this is where Cargo has to interact with the build system. That if C is my main application, then I have to bring in the Rust library effectively to link that in with. I build the Rust as a library and I bring that into my main application. But I saw straight away that's a real positive there. You look at other languages like the Pythons and the Javas that always have to dive out to Rust, and always this problem. If we can't do everything in that language, that's always going to be a problem. But also we don't want to throw away stuff we've already got. So we need a migration. If we were going to look at Rust, we would want a migration strategy, and having this interoperability does open up a certain amount. Now there are certain limitations there, and probably the biggest limitation at the moment of this interoperability is that the C code itself, certainly in what I've been looking at, would have to be built with the LLVM, the Clang-based model as well. I haven't tried linking that across with, say, a GCC build, but it's all, of course, based on the ABI. There is no reason it shouldn't, but it's based on a common ABI model associated with that. Now, I mentioned errors earlier. I said that the error management. So this idea of panicking. So here we've got a simple divide function in Rust. So it's the public function divide. It's taking those two 8-bit integers and returning an 8-bit integer associated with it. And of course, if the denominator happens to be 0, as it is on the right, then that program will panic. So divided by 0 gives us a well-defined panic again, which of course, again, in other languages in C, we don't know it's an implementation. It's actually some defined feature of what divide by 0 actually generates within that. So 2 ways Rust allows you to address this. First is it has a concept called optional. Anybody who's done modern C++ would also be familiar with optional. An optional has this idea, as the name implies, is I can return back an optional value. And that is either none, means I've not returned anything and I can test for that, or you wrap the result in something called sum. So at the higher level, it has these capabilities to check for none and sum. And if you've got sum, you basically can unwrap that value and take the real value associated with it. So that's certainly one type of interface. The other model is using, again, built into the language, is this thing called result. The difference, result is a little bit like the optional, but now it has 2 return values, one of those being the correct value and one of those being an error value. Now here I've returned 2 integers. We could return a string, we could return an object, as the error, whatever the error represents in here. So here you can see I can wrap the error value or the OK value. And again, there are tests you can apply for this. You can again have behavior dependent on whether you're having an error being returned or an OK being returned. And there's lots of models built, different models to build into that. So this is rather than using exceptions. And again, I find this interesting, but if you look at modern C++, that a lot of work that's been done in 17 and 20 has moved certain parts of the standard library away from using exceptions to using things like the standard optional model to again, because this doesn't have a runtime overhead, and it puts the responsibility of error management back in the programmer's hands, which of course is so important in the smaller embedded system. So what about embedded Rust? So Rust, again, is a systems language. It works perfectly on things like Linux. But what if I want to get down to my deeply embedded? So here you may be familiar. We use things like the Cortex-M series a lot in our system. And what I say is that there's great support out there. There's a community. I'd recommend having a look at that link there, the Awesome Embedded Rust. And there is well-defined support already for things like the Cortex-M. So you can see I've listed a load of chips there, the Nordic, NXP, etc. It's very community-led. There's a number of different abstractions. Again, this important as this heapless implementation. The idea of a customized panic. So this is, if my program is going to terminate in some way, I need a well-defined model in the same way that we have to deal with a C program terminating in some ways. And you can debug it using standard GDB. At the moment, there are no direct IDEs supporting Rust, but one thing you will find with Rust, of course, is you need to debug it far less because so much is done within the language itself. It also has built in, as part of the embedded Rust working group, they've created a set of abstractions. And they've got this idea of the embedded-hal. And this is, if people have worked on things like the ST chips, you'll be familiar with the ST-hal. And it's a very, it's again a very strong correlation with something like that, where you've got building blocks that are chip specific. So you have building blocks for things like the Cortex-M, but then you'd have building blocks sitting above that for a particular family like the STM32. And then you've got building blocks above that for example, the STM32F4, 07, etc. So it has a quite similar model to the way ST structure their libraries for their C support for the embedded application within that. And that means that if your particular HAL is supported, then out of the box, you can get up and running on a particular device immediately. And obviously there are formats there for building HALs and explaining how to build further HALs associated with that. So this is a very partial bit of code, but just an example. So I want to try out Rust on our targets. So we happen to use an F4. So anybody who's attending our C and C++ course will know we use the STM32F407 on those courses as our main core. And I've happily, very easy to get Rust running on those targets. And this is our, we know our hello world is flashing the LED. Now again, the syntax might initially look, well, but if you've used things like the ST-HAL, it's not dissimilar to using something like that. So we've got this thing called a prefer access crate. So there you can see the crate is already written for me based on the STM32F4. And those crates are created. There's actually a nice program that is taking people who might be familiar with the some of the SimSys model is using the SimSys SVD files to create these packs. So there's an automatic, so if there's an SVC file that exists, which is that debug file that's used a lot by things like Kyle, then these packs are automatically created based on that register. It knows the register, that defines the register layout of my particular device. And that loop is simply, we've got GPIO port D, we're doing the input data register, we're reading it, we're looking at the bit 9 and we're saying, is the bit clear? And if the bit is clear, then we're then writing to the ODR, the output data register, bit 9, we're setting it or we're clearing it. Now that syntax there actually is using one of the closures, but again, don't worry too much about the detail. That's one particular model that's out there. And then you can see the ASM delay. That delay is based on actually a cycle count delay within that. So to get that hello world working, was literally less than an hour from downloading it, getting it running and running on our particular targets under GDB. And that to me was a massive step forward in terms of the potential for Rust as a true embedded programming language. I should say, is also very important to me is the image sizes created by Rust were comparable to the C program. And that, again, I was nicely surprised that when I looked at the overall size of the programs, there was very little difference between the C image that was being created, and again, basing on a like for like using the ST-HAL and the C++. Now, again, you don't have to use these peripheral crates. You can go down to the raw level. Obviously, that's a dependence. So to wrap up, where are we? There's a very good book called Crossing the Chasm. I was introduced to this book by one of my mentors back in the early 90s. And this was a book that helped me understand why some technologies, really good technologies and technologies that I actually work with, didn't make it. So why do some things become popular? Why some things don't become popular? I mean, Malcolm Gladwell talks about a tipping point as well as a similar idea. So it's very much a marketing model. And what Geoffrey Moore brought together was this idea of this chasm. So you may be familiar with it. This is a marketing sort of chart that people use in terms of the adoption of technology or anything, not just technology, but anything. And you have innovators, you have early adopters, early majority, late majority, and laggards. And normally that's a single curve, a single sort of DOS distribution curve. What Moore brought out was, he said there was this big chasm sitting between the early adopters and the early majority. And the difference is that the early adopters sort of get it. They can look at something and they can apply that technology and say, I understand how that is going to benefit our business. They don't need it to be laid out in a data sheet. They don't need it to be laid out as a demonstration. They can extrapolate from, they can see beyond what they're being shown to see this. I can see where this is the immediate benefits. They don't need them directly to be explained. Where the early majority need that extra comfort and they need more proof of concept, they need a number of success cases to really get that feel that it's right for them and to take, because it's all about risk. It all comes down to risk. And the idea is the early adopters, by adopting early, they take bigger risks, but they would typically get bigger rewards because they're further ahead in these aspects. And one thing about the embedded industry is, because of the very pragmatic nature of deeply embedded, then a lot of embedded people tend to fall into the late majority. So Agile is a good example. We see Agile is only now becoming more accepted and more used in the deeply embedded space, where Agile itself has been around for 20 years and has probably been mainstream in a lot of the sort of web-based development for probably a decade now. And that's where we are with Rust. So there's certainly an early adopters. There's really good success stories in things like the hosted environment, in the Linux environment. The other nice thing is Rust plays very nicely with the web. So with things like WASM, again, not an area of expertise for myself, but it's got that benefit that it has all that web sort of support and that internet support as well. And my concern is that the embedded space, we tend to be the late majority within that. So that's why I'm saying that even if Rust does make that transition and gets into that early majority in the sort of Linux world, I still think it will be some time before we see major use of Rust in the deeply embedded space, just because of we tend to be that late majority within it. So where Rust excels is the two outstanding things when you use Rust. First is its memory management, this ability to guarantee that you won't have things like dangling pointers, you won't have incorrect references. It is such a safe memory model. And again, anybody who's done any degree of programming understands how powerful that is. And it's also memory safe from a dynamic memory. So it eliminates all of the issues apart from the one we can't eliminate, which is fragmentation, which of course is down to the actual implementation of the memory management itself. The other area that is really impressive, somebody who comes from a threading background, comes from a real-time operating system background, is its support for threading, especially in a symmetrical multiprocessing, multi-core environment. So simple things like the enforcement through the lifetime of mutex protection. So you cannot, so for example, having a global variable, you cannot directly access it without protecting it within that. Again, there are techniques, but so it enforces that, and it takes all of these problems straight on. Now that initially can be very frustrating because you feel like you're fighting the language, but all the time the language is just trying to stop you doing something potentially dangerous. However, those two things are not prevalent and deeply embedded. You know, we typically don't use dynamic memory for all the reasons associated with it. So MISRA, again, dynamic allocation not be used. You know, insufficient memory may cause failure. There's variance of execution times within that. And of course, at the moment, in the deeply embedded space, if we're using Cortex-M, we're not SMP, we're not symmetrical multiprocessing. We may be asymmetrical, we may have two Cortex-Ms in there, but they are separate images as such, so we're not using SMP. So that takes away two of the leading immediate benefits of Rust. If I was working on Linux today and I was programming in C on Linux today, then I think you've got to say Rust is going to be there. Other things that are going to cause challenges for the language itself. First is it's syntactically it's very different from C, and it's got I think a very steep learning curve, because it's a language where you sort of have to understand it all to write even quite simple programs. And this is because of the lifetime management. You know, people may be screaming at me saying that's unfair of us, but it's a language you do have to grasp it as a whole to get the best out of the language. You can do a certain amount of sort of C, you know, Rust in C or C in Rust as such, but actually to really start building non-trivial programs, you do have to get a feel for, you do really have to understand this lifetime management. And that's akin to sort of C programmers having to understand pointers, and so many people plateau at that area. So I do think that's a challenge for a lot of C programmers, is it's such a different syntax that adoption is going to be tough, you know, within that, unless it's presented in the correct way. However, there is a huge amount of resources out there, very, very good support as well. The other thing that may worry companies, or some people may look at it in a certain way, is Rust has a 6-week, what they call a release train. It's an agile model. And now this isn't a major release, but this is a minor release. Every 6 weeks, there is basically a new point release of Rust within that. And that obviously is to do with stability of the language. Now, of course, a lot of this is bug fixing. It was improving aspects of the language as well. And there are major versions, and the idea is that there's backward compatibility within that. So people, of course, have to look at that. Of course, we know that things like C don't, you know, they move, you know, they're glacial in terms of the way things like C move, and obviously C++ moves with a 3-year cycle as well. And Rust has this major 3-year cycle. Other thing, of course, is perceived cost. Is the work that would need to be done if Rust was going to be adopted. So the time people would spend learning the language and trialing and doing those, and obviously that's a direct cost. And unless that can be correlated and related to savings, which we're not very good at doing, then it's going to be hard to argue that particular case. So it really, again, it's back to this thing where the early adopters understand that because they can see where those cost savings are going to be. And then obviously it's interesting with Microsoft talking about 70% of their bugs. Other areas, I think the fact that in the embedded space, with a lot of people were very dominated by IDEs. In my experience, going around to companies and working with companies, so tools like IR, very, very good, been around for many decades. Kyle, obviously Sega and ST have their own tools as well, and Eclipse, and people are very familiar and sort of wrapped in this environment of programming in C in that sort of tool, and having to become more familiar with working outside of that. Now, one of the upsides, of course, there is the growth of Visual Studio Code as an IDE, as an editor, is there's very good support for both C and C++ in there, and Rust as well. The other question is, if I'm using C and I'm using MISRA and I've got static analysis and I'm using testing tools, is that going to be enough if I'm not using dynamic memory and I'm not using SMP? And you're going to be a long way there. But there's still certain aspects of the program that, or of the runtime lifetime management, that it's very difficult, even with those in place, to detect. You're still going to get problems. And of course, MISRA, you're investing in MISRA tools, you're investing in dynamic testing tools as well. And in a sense, they become free with Rust, which takes me on to my next stage, which of course is, for many companies, free open source software is just not, they're not prepared to work. They want professional tools that they can perceive. They want to buy those tools in. Now, of course, people using Linux are more familiar with that because they tend to be using GCC. And obviously, there are a number of companies out there using things like the ARM GCC compilers, which are free and everything else. So I think if you're using ARM and GCC today, that's less of an issue. But if you're, say, using something like IR today, then I think, again, that's what I call a political challenge more than a technological challenge in many ways. The other area is obviously the use of real-time operating systems. A lot of companies are using, I mentioned VxWorks, FreeRTOS, things like Integrity within that. Now, Rust does have bindings to, you can obviously create C bindings, so it does have bindings to FreeRTOS. There is a runtime example with Rust called Real-Time for the Masses as well, which is a nice, simple sort of free RTOS as such within there as well. But that, again, is an adaptation where you've got systems built on that. They are going to be further challenges. Finally, two others. As a program becomes more popular, then bigger companies are going to get involved, and of course, bigger companies may want to profit from this. And the one that sort of was a bit of a head slap moment when Microsoft put out there that we're creating a new Rust-like programming language for serial coding, and it just, every part of you wants to scream, going, why not just use Rust? And of course, we had the same sort of similar issues with Java and C# came through at that particular time. So if you want to look at this thing called Project Verona and see where that goes, but that is a worrying that obviously Microsoft they are such a big player. If they create something similar, is that going to be problematic in the same way that C# was, and is of course only then running on a Windows-based platform, where Rust runs on every platform within that. The other one, which has been quite interesting, is this concept of unsafe. Now, unsafe is a double-edged sword in the fact that it's probably the most important part of embedded Rust. And what unsafe does is give you the ability to program as you would in C in Rust. So what it does is turn off all of the Rust checking. So you can do raw pointers, you can do register manipulation, everything you'll be doing at raw C. So all the raw pointer stuff you can do in Rust if you want to. And that's how that embedded-hal is, of course, built on top of unsafe aspects within that. But you have to explicitly wrap that code in unsafe. You're going to do certain things. The danger there is, and what we've seen is that if that's not managed, then of course it becomes a go-to for people who are fighting, say, the lifetime management Rust is called the borrow checker. If people start fighting that borrow checker rather than understanding how to program around it, they will just resort to using unsafe because, well, now it compiles within that. And I think that definitely, in terms of coding guidelines, is the biggest area of Rust that has to be addressed, because I think if it's not managed and you don't have a professional viewpoint of a language, it will become too easy to then eliminate all of the benefits you're getting from the language in the first place. And I like this. This was off one of the user groups. I saw this. This was a Java programmer posted that, which said, guys, how are you able to understand such a complex programming language? You're all engineers. And my answer to that is, well, yeah, it is an engineering language. And I think that's what attracts me to it as a programming language is we talk about, or we try and define, what does the term engineer, software engineer means? And to me, it's beyond any language, beyond any syntax. It's really saying, what are we trying to do? How can we create safe, reliable, robust programs with the tools we have? And this is another tool in the toolbox, and it's certainly a very, very powerful tool. But it is a challenge, and if you're not, if it's not a hacker's language, not language you're just going to pick up. I think it really is a language that is a fantastic engineering language, but I think a lot of people will be put off very quickly initially by the syntax, because it will seem so different and so challenging to see. C is easy to learn, that's its strength, but incredibly difficult to master. Rust is much harder, and it's, and I think maybe it's my Ada background coming out. I see much greater parallels with using Ada and learning Ada in the 80s and working with Ada in military systems, and the challenges Ada gives you. The similar ones there, and more so in Rust as well within that. So I thought that was great. It sort of so to summarize, where do we sit today? Well, a lot of people are just going to be happy with C, and I think that that's just a reality for the forthcoming future, is that we won't see a wholesale move to Rust from C. People are working on that today. There's an investment there. Hopefully, people are using static analysis tools. I'm still, amazed how many aren't within that. And obviously, there are very, we should be using professional testing tools, professional verification tools in there. I suppose where Rust would sit today is those companies that are possibly looking to transition from C. And of course, at the moment, most of those are transitioning. We certainly see it to modern C++. So there's and by modern, we're now up to 20 is on imminently, and they're already working on 23. And there's a lot of really good stuff. C++ 17 is a safer programming language than C. It brings many of these ideas in there, but it can't inherently be as safe as Rust. So that's probably where I see it would sit today, is if you're looking at transitioning from C, the companies looked and saying there are, from a safety perspective, from a security perspective, from a robust perspective, we feel it's time to move away from C. Then I think Rust should be looked at as a language. There is support there today, and there is a community there, but I think it will come down to the companies. I think it will come down to where you sit on that adoption curve as a company, and most companies being the late adopter are less likely to take that risk associated with it. Certainly if you're on Linux, then I would say today, go and look at Rust, go and play with Rust, go and understand it. It is very, very different, and all I can say is it's an engineering language in that. So thank you very much. I hope you've enjoyed today's webinar.